Okay, 12.2 is our first really exponential modeling. Well, I don't know our first, but it's an exponential modeling problem, and it's like a real example. So they're saying, let's say we have light on an ocean, and the intensity of light on the surface of the ocean is I0. Zero means it's zero depth, right? Intensity I at zero depth. So our intensity then function would look like I is equal to I0. This is part A, I think. Intensity is I0, and then it's an exponential function with depth. So base to the D, where D is how deep you are, right? So as you go deep in the water, the light gets dimmer. And eventually, really deep, it's completely black, completely dark. So we need to find B, because we know this is the intensity. On a sunny day, this is going to be a brighter number, and a dimmer day, it's a less number. But whatever it is, it gets smaller as B to the D. Now we know it's going to get smaller. The depth gets big, so this number is going to be less than 1, or else it's going to get brighter. So we know that our B has to be less than 1, our base has to be less than 1. Okay, now then they tell us that it goes 15% for every 3 meters. It decreases by 15% every 3 meters. So we have to use that data point. So if it decreases by 15%, we know that at 3 meters, instead of the intensity in the surface is I0, it's going to be 15% less than I0, right? If it starts off at I0, 3 meters down, it's 15% less, or it's 85%. So, and normally, 85%, we like to talk in percents, but we got to put decimals into here. So the intensity at 3 meters down is going to be 0.85 what it is at the surface. Right, 15% less than what it was at the surface. So 0.85 is equal to I0 B to the 3 because it's 3 meters down. Now, clearly the I0's cancel. So whatever it is at the surface doesn't matter. So now we have 0.85 is equal to B to the 3rd. We want to know what B is, right? We got to get rid of this 3 here. But that's not so bad. We just take to the 1/3 power on each side, right? So that works. So we can do that. We can go to the 1/3 power. Let's see, is there a way we can use, yeah, that's probably the best way to do it. So let's raise both things to the 1/3 power to get rid of the 3 to the 1/3. So now we have just the base, right, to the 1/3 is equal to 0.85 to the 1/3. That's going to be a calculator problem. So 0.85 y dx 1 divided by 3. I get 0.947268. How many decimal places to keep? Let's say 0.947. 0.947. So now you want to keep a lot of decimal places for bases, because when you start multiplying it by itself many, many times, it makes a big difference. So always keep lots of decimal places, or else everyone's going to get different answers and stuff. So I'm going to keep lots. So I'm going to say 0.94727. So 0.94727. Okay, so our model then is the intensity is I0 0.94727 to the depth. That is our model. Now we know how deep it is anywhere we want. And again, it makes sense. The number is less than 1. The more we multiply it, the smaller it gets. Yeah, that's exactly the number they chose too. Cool. Okay, then part B is easier. I'll let you figure that on their own. They're just saying, okay, how deep do you got to go till it's only 1% of its surface intensity? So the surface intensity is only 0.1%, which means 0.01 I0, right? 1%, 0.01 of the surface is equal to I0, our base, 0.94727 to the depth. So we need to figure out what D is here. So of course the I0's cancel, which is nice, doesn't matter what that is. So we're gonna have to figure out D. And so what do we have here? 0.01 equals 0.94727 to the D. So how do we get that d down from up there, right? We want to know what d is. I guess we could do guess and check, plug in different numbers until we get 0.01 out, but that's pretty lame. So how do we get d out of there? I guess we could raise both sides to the 1 over d, but then we have a 1 over d over here, right? And then we get rid of that, and that's almost worst, right? So the way you get rid of an exponent is you take the natural log, or any log. I like using the ln natural log. It's easier to write, right? Only 2 letters. Take the natural log of both sides. ln of 0.01 is equal to ln of 0.94727 to the d. And remember that, oh, if we have the ln of something to a power, we can put the power in front. So this is just ln of 0.01 is equal to d times the ln of 0.94727, and I guess I could have put parentheses there to show that. But again, log of something to a power, you can put the power in front. Now we can solve for d. This is just a number you plug into your calculator, so it's this divided by that is equal to the depth. Okay, so here again is how you need to use your logarithms, these power of logarithms, to help you solve problems like this. So it's a very useful thing to have. Excellent.